Good morning. In the previous lectures, we have seen different transistor connections, namely common base transistor connection, common emitter transistor connection, and a common collector transistor connection. Out of these three transistor connections, we have seen that common emitter transistor connection is the most commonly used one because of its high current gain, voltage gain, and power gain, and also it provides moderate output to input impedance ratio. So in 95% of the transistor applications we will use common emitter transistor connections. And one of the important application of a transistor is it provides the amplification of a weak signal. And here we will discuss about the transistors and amplifier in common emitter arrangement. For that, let's consider the diagram given here. The circuit, which is a common emitter transistor amplifier, and here we have used a source of voltage VBB, which forward biases the base emitter junction, and VCC, which reverse biases the collector junction. The input is applied in the base, and we are considering the input in the form of a sinusoidal function. The input is represented here, and output is taken across the collector resistance RC connected in the output circuit. Now, if there is no VBB is connected in the circuit, then during the negative half cycle of the signal, the base will be reverse biased, which will upset the transistor action. So this voltage source VBB ensures that base emitter junction is always forward biased. So this voltage is called bias voltage. So we will call it as a bias voltage. Now, during the positive half cycle of this signal, the voltage across the base and emitter VBE will increase, and which in turn will make more electrons to flow from the emitter to the collector, which will increase the collector current IC. This increased collector current flows through RC, which makes a greater potential drop across the output, so that we will have a greater output signal during the positive half cycle. And during the negative half cycle, the base emitter voltage will be decreased, and which in turn decreases much the collector current than the previous case, so that we will get an amplified signal as shown by this diagram, the second diagram. Here, if we analyze the collector current, we can see that when there is no signal is applied, that is when input signal, let's call it as V in, is equal to 0, still we have a collector current IC, which is can be written as beta into IB. And this collector current IC is due to the voltage source connected in the base emitter junction, that is due to VBB, and this collector current flows through the circuit even there is no signal is applied. So this collector current is called zero signal collector current. Zero signal collector current. So when VBB is connected in the circuit, which ensures that base emitter junction is always forward biased, which provides a collector current even in the absence of the signal, and that collector current is called zero signal collector current, and definitely no doubt it is a DC current. So we will represent it by IC. Now when the signal is applied, there is a current which flows through the collector due to the signal alone, which is purely a AC signal. So it is represented by this letter small IC. So the total collector current flowing through the collector circuit will be IC equal to the sum of the zero signal collector current plus the collector current due to the signal alone. So this expression represents the total collector current in a circuit when signal is applied. So remember this condition that zero signal collector current is essential to ensure that base emitter junction is forward biased. And from the output diagram you can see that about this zero signal collector current, the variation of the output current, that is the collector current, occurs. Now when we are considering a common emitter transistor circuit, some of the different voltages and currents which we will come across will be discussed in this table. If you consider the emitter current, then I'm rewriting it here. The emitter current, the instantaneous emitter current is represented by IE, and the DC collector current is represented by IE, and the total collector current we are representing by this I, the capital subscript E. So this all make the different notations for the emitter current, and this first one represents the instantaneous AC, that means the emitter current due to the signal alone, or the contribution of the emitter current from the signal, and capital IE, this one represents the emitter current due to the DC conditions prevailing in the circuit, because there is emitter current due to the DC conditions of the applied voltages, we call it as the bias voltages, and there is a total current which will be the sum of these two currents, and that is represented by small I with capital E subscript. Similarly, the collector current due to the signal alone is represented by IC plus the zero signal collector current, that is the collector current from the contribution of the bias voltage is represented by capital IC, and the total collector current is represented by the small I with a large or capital C as the subscript. And similarly for base current, we can have this representation. Small ib represents the instantaneous value or the AC component of the base current, and this ib represents the DC component of the base current, and this one represents the total base current. And this is same for the different voltages, that is the two important voltages in a transistor circuit are collector, and in the case of a common emitter transistor configuration is collector emitter voltage, that is VCE and VBE. Here also VCE represents the collector emitter voltage due to the AC signal. We can call it as the instantaneous value of collector emitter voltage. Then collector emitter voltage capital VCE due to the DC sources, and the total collector emitter voltage. Similarly, the another voltage, which is the emitter base voltage, emitter base voltage VEB. This one represents the instantaneous AC voltage, that is the voltage appears across the base emitter due to the signal, and VEB, which is due to the base emitter voltage due to the DC source is connected in the circuit. Then this one VEB represents the total base emitter voltage. So these are the different notations which we will use further in this discussion of transistor amplifiers. So when we are using the proper notations, try to understand which is it a DC voltage alone, or is it a combination of signal and DC sources applied, or it is due to the signal alone. So remember these notations. Now we know that the important parameters or important thing in the case of a transistor connection is its characteristics, the input and output characteristics. And the output characteristics provides the variation of in the case of a common emitter transistor connection, it provides the variation of collector emitter voltage with corresponding collector current IC at constant base current IB. And this is needed because the collector current actually determines the output current, which determines the amplification factor in the case of a common emitter transistor connection. So how this collector current varies with a collector emitter voltage is a very important parameter or important thing in the case of transistor connection, and this is established by plotting the output characteristics. But there is another important way in which we can represent this collector emitter voltage with the collector current, or the relation between the collector emitter voltage and collector current, and that is what is known as the load line, the transistor load line, which is the far simplest than drawing the output characteristics. So in most of the practical situations we will use this load line instead of output characteristics. And if we come to this diagram, the one on the right, you can see that this way these curves represent the output characteristics with VCE is along the x-axis and IC along the y-axis. Now let's consider a transistor circuit with no signal. So we are not applying any signal, so signal is 0 here. So the circuit will always have the DC conditions. So the different currents and voltages in the circuit are capital IB is the input current, capital IC is the output current, and VC is the voltage across the collector, emitter, and VB is the voltage across base emitter junction. Now for this circuit, let's apply Kirchhoff's voltage law to this output circuit, where we are connected a output resistance RC to take the output. So if you apply the Kirchhoff's voltage law to the output loop, here we are having the voltage source VCC. So if we start from here, then go like this, then we can write VCC VCC, the collector current is flowing towards the collector, so it is we are moving in this same direction as that of the collector current, so it is minus IC RC minus VCE is equal to 0, or we can write it as the collector emitter voltage VCE is equal to VCC minus ICRC. Now for a particular circuit, this VCC and RC are fixed, so we will have a linear relation between VCE and IC. If we plot this one, VCE versus IC, it will be a straight line with negative slope, and that is represented by the line AC in this diagram. So this AC represents the relation plotted on this curve, that is VCE is equal to VCC minus ICRC, represents a linear relation that can be drawn or plotted, and it represents the equation for a straight line with a negative slope. So we will have a line like this. Now we have to determine the two endpoints of this straight line, A and B. It is very easy to determine these two endpoints. For that I am considering at end A we can say that VCE is equal to 0. Now Remember this expression always. VCE is equal to VCC minus ICRC. We are going to use this relation for the next discussions. So VCE is equal to 0, then above equation become VCC is equal to ICRC, or IC, the value of IC for which VCE is 0 is given by VCC by RC, which is the point represented by A. The importance of this point A is that it is the value of IC for which VCE is equal to 0. The point A is actually corresponds to VCE is equal value of IC for which VCE is 0, so we can write it as VCC by, we obtained it as VCC by RC. And now to find the point B, the point B is the point or the value of VCE for which IC is equal to 0. So put it here, IC is equal to 0, then above equation become VCC is equal to VCE, or we can write it as the value of VCE for which IC is 0 is equal to VCC. So this point B is actually the value of VCE is equal to VCC. Now we can say that this DC, we call it as the DC load line because we are considering only the DC voltages, so we can call it as DC load line, gives the same information as that of that given by the output characteristics. So the points on A and AB, the line AB will represent the corresponding values of IC to corresponding to VCE for a particular values of RC and VCC. So the importance of DC load line is that it gives or it provides the same information as that of or as that given by output characteristics. So you can see that output characteristics will be different for different base currents. So for different values of base current, we will have different values of collector currents with respect to the collector emitter voltage. But if we draw the DC load line, we will get the values of collector current for different values of or corresponding to the collector emitter voltage for different values of IB. So if we fix the circuit by providing or connecting a particular VC voltage source of value VCC and a collector resistance of RC, then the DC load line gives all the possible values of collector current with respect to the collector emitter voltage. So which is DC load line is a substitution or an alternative way of determining the variation of IC with the VCE for a common emitter transistor connection. Now Another important thing is that these are all the curves represent all these curves represent the output characteristics, that is will be true for or all connection, or we can say that this will be for particular IB. Let's say this IB is 5 microampere. This is for 10 microampere, and let's say this is for 15 microampere. So when we vary the base current, we can have the different output characteristics. Similarly, this load we can have the load line for a particular value, a particular circuit. Now this zero signal collector current values and collector emitter voltages are known as the operating point. This zero signal collector current and collector emitter voltage is known as operating point, because about which this variation of output voltage will occur, or collector current and collector emitter voltage variations will occur. Now it is also called this zero signal collector current and VCE collector emitter voltage is otherwise called operating point, is otherwise operating points, is otherwise called quiescent point or silent point or Q point. Since it is called silent, the reason for calling it as silent point is that it is the values of collector current and collector emitter voltage when the circuit is silent. Silent means there is no signal applied to the circuit. Only DC conditions are existing in the circuit, then we can call the circuit to be a silent. So the operating point of a transistor is otherwise called a quiescent point or operating point. Now if we consider this output characteristics of this transistor for my base current of 5 microampere, then this line represents the possible values of VCE and IC. And also we have seen that this line AB represents the DC load line, which also gives the VCE and IC values for that circuit. Now the only point which satisfies these two conditions, that is the points on the output characteristic and the point on the DC load line, is the point Q. That is the point which satisfies the conditions given by the output characteristics as well as the DC load line, is the intersection of these 2 points, and which is the operating point. So the operating point can also be defined as the intersection of output characteristics and DC load line. So the operating point of a transistor connection is determined by finding the intersecting point of output characteristics and DC load line. Determining the operating point is important to check the transistor actions. Thank you.